All right, we're continuing with section 14.2, and I'm on page 921, and we are going to do number 24. So in exercises 22 through 29, change the integral to an iterated integral in polar coordinates and then evaluate it. And they give us the integral from 3 over root 2 to 3, and then from 0 up to the square root of 9 minus x squared. Uh, 1 over the square root of x squared plus y squared. Dy dx. All right, so our first order of business is always to sketch our region R. So let's sketch the region, and then we'll switch it to polar coordinates. So our y. So y goes from 0 up to the square root of 9 minus x squared. So that's y equals 0. Down here is just the x-axis. And then y equals the square root of 9 minus x squared. That's just a semicircle with radius 3. All right, so where this is 3 right there. And then, so y goes from here to here. X goes from 3 over root 2 to 3. Whatever, 3 over root 2. So, I don't know, like, put it right there. 3 over root 2 up to 3. So our region, R, is that region right there. So now we have our region, and they already had it set up for us in terms of being a type 1 region, function to function, constant, but we're switching to polar coordinates entirely because that's what we were told to do in this problem. And to try to integrate this in rectangular coordinates, you run into some issues. So we're just going to switch to polar coordinates. So now there are a couple of different ways we can go about doing this. I think the easiest way is that we already have our sketch. We could just write down what these are and switch to polar coordinates that way. So for instance, we could have just said, okay, this is x is between 3 over root 2 and 3, and y is between 0 and that. And we'll use this information still as square root of 9 minus x squared. That's what that said. And that's the picture that we have that corresponds to this. Now you could go through and say, okay, well, x is equal to r cosine theta, y is equal to r sine theta, substitute all that stuff in, and we will do some of that here. But it's good to have that picture along with that. So when I look at this picture, I can see my radius varies from, I don't know, something here up to 3. The biggest the radius is 3. So I can kind of see that in my picture immediately, but we can squeeze that information out of here as well. So let's look at what we get at from y equals the square root of 9 minus x squared. So you can see how to do it converting using the algebra as well. So I'm going to do this 2 different ways. So y equals the square root of 9 minus x squared. So first off, I'm just going to switch everything to polar coordinates. And that's what I'm going to tend to do most often, just because I want you to get accustomed to working with polar coordinates. So here, y is equal to r sine theta equals the square root of 9 minus x is r cosine theta. So we have r squared cosine squared theta. And we square both sides of this, and we end up with r squared sine squared theta equals 9 minus r squared cosine squared theta. And move everything over to the left, and we get r squared cosine squared theta plus r, not everything, everything with the exception of the 9, I'm sorry. R squared sine squared theta equals 9. And our favorite trick identity tells us this is r squared equals 9. And r always has to be greater than 0. So that's greater than or equal to 0. So that says r equals 3. So we could have gone through and gotten that way. Or you could also square both sides here. Y squared equals 9 minus x squared. And this is a more familiar realm to work in, which is x squared plus y squared equals 9. This is what we basically did in our head to get that we had that semicircle up there in the first place. Now, this on the left side, now we switch to polar coordinates at this point. Instead of switching at the very beginning, this is r squared equals 9, which tells us r equals 3. So regardless, wherever you switch to polar coordinates, you're going to get the same thing. So we get r equals 3, which wasn't hard for us to figure out in the first place. Now let's look at what we get for polar coordinates from these x values. So I didn't do the r times sine theta equals 0 part over here, but we'll look at let's look at what we get from these x's first. All right, so first, or I'll just do these simultaneously. So r cosine theta equals 3 over root 2. So r cosine theta equals 3 over root 2. And the other one is r cosine theta, equals 3. R cosine theta equals 3. All right, so now here, this gives us that cosine theta equals 3 over r times root 2. And this gives us cosine theta equals 3 over our r that we have. All right, so now we take this r equals 3 and put it into these, and this one tells us that cosine theta. And let me actually point out in our picture what it is we're looking at. Why did I put in r equals 3? So when x equals root 3 over root 2, so when x equals that, I'm just looking at, when I put in r equals 3, I am only looking at that point right there. I'm not looking at any of these other points. And when I put in when x equals 3, and I put in r equals 3, I'm looking at that point right there. So I'm just figuring out what is this theta, which I see what that theta is, it's 0, and what is that theta, and we're going to figure out what that theta is. So that's why I'm putting in the r equals 3, because r actually varies when the radius is, let's say for instance, right here the radius is 3, but right here the radius, I don't know what that radius is. It's not 3 though. I can tell you that much. If I go out further, it's 3, because remember we get all of this reaching in. So this radius kind of varies in here. So I just want to figure out what that theta is, and I know what that one is 0. But more so, I want to figure out what that theta is right there. So when I put in the 3 right there, I get 1 over root 2, which tells me that my theta right there is pi over 4. And then over here, when I put in the 3 right there, let's do this so we can separate our work a little bit. When I put in 3 here, I get cosine of theta equals 1, which tells me theta equals 0. So I see what my theta varies between. So theta varies between 0 and pi over 4. And the 0 wasn't an issue, it was the pi over 4. We have to just figure out exactly what theta was there. So now we have what theta varies between, we need to figure out what r varies between. So now let's go back up to our picture. When we go back up to our picture, we have these different, and I'm going to stop my radius at this line every time. I'm not going into my region. I could go into my region, but I'm not going to. So right here, my radius is 3 over root 2. Right there, something else. And right there is something else. And right there is something else. And right there is something else. And right here is 3. So notice the radius, I was changing my theta. So the radius is a function of theta. It varies depending upon what your theta is. And it's going to vary from whatever these numbers are all the way up to 3. It's going to hit every number in between them. So down here at theta equals 0, it varies from 3 over root 2 all the way up to 3 and hits every number in between there. So now, how do we figure out what is this r as a function of theta? I'm going to use that point up there again because I know some information about that point. I know that there theta is pi over 4, so I can use that. I know that pi over 4, x is equal to y. There's some other ways we could do that as well. We could also use this to figure that out. We take our x, which is 3 over root 2, and plug that in here, and you're going to get y is also 3 over root 2. So you can get it that way. You'll get x is equal to y, excuse me, and then we'll figure out our r that way. So we have r is 3, we have theta goes there, and now we need our other r. So let's separate our work one more time. So now here, what I'll do is when theta equals pi over 4, one more time at the picture. Notice when theta equals pi over 4, I'm at my x is 3 over root 2. And we know from trigonometry, when theta equals pi over 4, that x and y are going to be the same thing on this circle. So that means that y is also 3 over root 2. So theta equals pi over 4 gives us that y equals x, which is 3 over root 2. But y, we know in polar coordinates as r sine theta equals 3 over root 2. Now careful here, before we plugged in r equals 3, we don't want to do that here, only because we're trying to get all of these r's, not just that one right there. We're not just looking at r equals 3, we're trying to get all of those. So we don't want to plug in 3 right now. So we're trying to solve for r. We're not trying to substitute an r in there because we already have what theta is. So we're trying to solve this for r. So r equals 1 over sine theta times 3 over root 2, which equals 3 over root 2 times secant of theta. We know that r should be a function of theta. So now we're finally ready. We have r goes from here up to there, and theta goes from here to there. So now we finally have our region r. So our region r that we're considering is r equals the set of points. And there are a bunch of different ways you can go about doing this. Like I showed you all how to find the r equals 3 in 2 different ways. There are different ways you can go about this, or you can just use your intuition. I'll always go through the algebra steps, even if we could look at a picture and try to tell stuff, sometimes we may have difficulty coming with the picture. So I'll always go through the algebra as much as possible. Down here, I did this at theta equals pi over 4, but again, I could have just used this. I could have used y equals the square root of 9 minus x squared and plugged in there 9 minus x is 3 over root 2. So 9 minus 9 over 2. And I would have gotten the same thing. Y equals 3 over root 2. And then substituted y equals r sine theta in there. And we would have gotten this exact same thing. All right, so r comma theta such that, now what do I have? Theta is between 0 and pi over 4. And r is between, which one's at the bottom? This one was the one at the smaller of the two. So 3 over root 2 secant theta all the way up to 3. All right, and now we can go ahead and set up our integral, and we can't forget to change our integrand to polar coordinates. So the integral becomes the iterated integral from 0 to pi over 4 and from 3 over root 2 secant of theta to 3. So our integrand was 1 over the square root of x squared plus y squared, but we're switching to polar coordinates, so the square root of x squared plus y squared is just r. So we end up with 1 over r, and then remember we're integrating in polar coordinates. You have to put that r there, and then dr d theta. That's fairly straightforward to integrate that. All right, so I'll stop this video here, and if time permits, I'll go over the steps of actually evaluating the integral for exercise 6, which I skipped, but I've set the integral up though.